Is that the last talk for this morning? So Vladimir Kazakov from Paris. He's going to talk back from characters to quantum superspin trains by fusion.
Hello, it's very nice to speak here in Cambridge, and thanks for the organizers for inviting me. My talk will not be about the integrability in ADS CFT, although I embarked onto this subject because of my poor understanding of quantum spin chains, maybe, and the desire to improve the understanding, and also to invent maybe some new interesting approach to the quantum spins in general, to the quantum spin change in general, and also to generalize everything to the super spins, where due to the complexity of representation theory, the situation is a bit worse than for the usual bosonic spin chains. So I will report the fruits of this work during essentially the last year. It will be the results of two papers, one with Pedro Vieira, very recent paper with Pedro Vieira, who is present here, and the second with Anton Zabrodin and Alexander Sorin at the beginning of the year. So the motivation for me to make this detour from ADS CFT integrability was my fascination by the idea that classical and quantum integrability are intimately related, and not only through the classical limit, which is normal, but also in many occasions quantizations means discretization. And these people understood in the 90s that actually the quantum properties, the properties of quantum spin chains, can be encoded into the fusion rules if you take all of them and try to write some equations on the fusion of particles into bound states, etc., similar to the ones which we are using also now in ADS CFT correspondence after the work of Nick Dory. So actually these dynamics of fusions can completely define and restrict the quantum properties of spin chains. And more than that, quantum spin chain can be completely described by the discrete classical Hirota dynamics. Hirota equation, I will speak about it. It's the master equation of the integrable dynamics for the fusion of quantum states. And all this in accordance with representation theory. In fact, it's a fusion of representations, smaller representations into the bigger ones. So it seems to be paradoxical, but the quantum integrability is just a subset of classical integrability, although you have to discretize, of course. You have to have the discrete classical dynamics in order to describe completely, I insist, the quantum spin chains. Okay, we don't go that far as to say that we fulfilled the dream of Einstein, at least for the integrable world, but it sounds at least as a nice joke. So I will show systematically that we can study quantum spin chains by the methods of integrable discrete classical dynamics. All this is all this approach, including these people, is heavily based on a very beautiful formula, the so-called Bajanov-Reshetikhin formula. To my surprise, even people who work on integrability sometimes don't know it, but it really encodes all possible fusion processes into a simple determinant formula, which is very similar to the character formula, to the formula for characters, so-called Jacobi-Trudy formula for characters. It's just its quantum generalization, let's say. So the main subject of our work with Pedro, and probably of this talk, is the direct proof of Bajanov-Reshetikhin formula. To our surprise, it was absent. At least the direct proof was absent in the literature, although we really looked hard into the literature, and we want to fill this gap by this work. I must say that mathematicians, in particular Cherednik, invented some more general constructions in the 80s, and they insist that this formula is a part of this more general construction, but we were unable to see this formula and to understand this construction. Probably it's to be understood. Probably mathematicians in some sense understand it, but it's nice to have the direct proof, and it might teach us something about quantum spin chains, especially that I'll use partially the motivation to do this work for me was my hatred to the multitude of indices in the nested beta ansatz and in the algebraic beta ansatz in general, and I wanted to get rid of them and to get back to the notions like characters, invariants, matrix differentiations, all this which is there to the heart of old matrix modelist. And I think this approaches matrix models and these quantum spin chains might be very close to each other, as was expected for a long time. And maybe our paper, our work is a hint on it. Actually, another motivation is to generalize it to supersymmetry, and it appears to be even nicer, and since it's more general, it appears to be nicer with supersymmetry, all this stuff. And even we discover not only we build all possible TQ relations for the superspin chain in our paper, the Baxter TQ relations, but all their multitude. I will give you the general formula at the end. But we also observed that just for supersymmetry case, because of more general structure, you have new QQ type relations between Baxter functions, Baxter Q functions, which I will also present. And all this presents a nice alternative to algebraic beta ansatz, since we can go now all the way from R matrix, from the basic R matrix to the nested beta ansatz equations by a very different path. Then, okay, now I start from things which most of the audience probably knows very well. Just the elementary R matrix for the SL. I will use mostly GL K/M superalgebra. Here it is. It's U spectral parameter times times the product of unities in physical space, which will be always vertical, and the auxiliary space. And the second term is built out of generators of SL K/M, just standard generators, as direct product in these two spaces. Minus sign appears only for supergroups, for superalgebras, and it just corresponds to the parity of the index alpha, whether it's bosonic or fermionic. Okay, then it's well known for many years that these are matrix. I will mostly speak about this I will speak only about this kind of the R matrix. It is satisfied the Young-Baxter equations, which are called sometimes triangle equations, so probably most of the audience knows what it means, this picture. I will not dwell on it. And the next step of our construction is to introduce already a fused R matrix. In this case, I remind that we have the auxiliary space in this horizontal channel and physical space here. We still have the vector representation in the physical space, but arbitrary representation in quantum space. And the R matrix looks very similar. Here it's just U times 1 in the auxiliary space times projector in the corresponding representation of auxiliary space. But here we have the products of generators in the physical space. Again, the standard generator of vector representation, and in the quantum space it's an arbitrary the generator in arbitrary representation lambda. That's already some calculation to do to prove that this object is nice and that later the transfer matrices built on it by it will be commuting, etc. But the idea was also invented in the 80s. You do some fusion, so you multiply a few R matrices in the along the physical space. So each crossing here means R matrix, and then you introduce the projectors on the left and on the right in this horizontal space, just projectors to the representation lambda. But you insert it in such a way that they are constructed also from R matrices in particular points. For that you just have to choose the spectral parameter to jump by 2 every time on each leg, u plus 2, u plus 4, etc., which of course imitates the structure of bound states in the theory. Then you observe that a couple of R matrices here are projectors, symmetric projectors, and it's enough, for example, for the case of 3 vector representations to symmetrize it and to build the symmetric representation, the third rank tensor of the symmetric representation. And since the construction is completely from R matrices, you can use Young-Baxter to prove various theorems, in particular the commutativity of transfer matrices, which I will come to it. Now, the next object is the monodromy matrix. We multiply already this new fused R matrices, this R matrix, along the auxiliary space where the representation lambda runs. Physical space are always vector, and a new element in this construction, we twist the monodromy matrix. We introduce just the group element in the corresponding representation lambda. We multiply from the right. It doesn't spoil Young-Baxter, by the way, when you introduce such a generalized R matrix, just because of the general group invariance, GLK/M group invariance. So this is this element. If you diagonalize it, you'll have 2 sets of eigenvalues, from x1 to xk and from y1 to ym, as usual for supermatrices, with some rotations here, it's general rotation omega. Okay, now the next step, of course, to put the periodic boundary condition, but twist it now, and to take the trace of monodromy matrix, which is called the transfer matrix, of course. This is the main objects out of which you can extract the Hamiltonians, including maybe the only single possible local Hamiltonian here. If you carefully, if you take the logarithmic derivative of t in a special point. But we take always the most general route, and our chain is inhomogeneous with arbitrary spectral parameters to make it as general as possible. Okay, then as I said, you see that we introduced the twist. It's the twist which physicists often use for specific physical situations in quantum spin chains. And here, actually, this twist plays a very important role in our construction. It's a new parameter, a new very nice parameter in the theory, the group element, and just operating with it, we can reformulate the whole stuff in sort of a matrix language.
Representations in the auxiliary space, or
which representations? In principle, typical also.
so
It's
although
general
you
enough.
send your Young tableau, well,
Here, of course, I just give it. I just demonstrated that here we have general Young tableau, and here we have vector Young tableau with one box, each physical representation. But I will comment on it later, very briefly. But I will show how the Young tableaus, super Young tableaus, look like when I will speak about Hirota equation. Okay, so this commutes with transfer matrix commutes for arbitrary spectral parameters and arbitrary representations lambda. Okay, so you have to have this image of Young tableau which lives on the auxiliary space. The same kind of fusion can be done in physical space, but I don't speak today much about it, although we have done this general construction for physical fusion also with Zabrodin and Sorin in our paper. Okay, now we come to the heart of this approach, the Bajanov-Reshetikhin fusion formula. This is a very simply looking formula and very beautiful one. It says that the transfer matrix in an arbitrary representation lambda, like you have here, this representation lambda, can be built as a determinant of transfer matrices in only symmetric representations. Here, T with the subindex, say Ts of U, is just the transfer matrix in symmetric representation in this one, which we sort of constructed here. It's very easy to see how this construction renders, in the case of lambdas, only one row, how it renders the correct result. Okay, I remind that the representation will be defined by highest weights from lambda 1 to lambda a, which are essentially the length of the rows in the Young tableau, in the super Young tableau or Young tableau. The formula actually looks the same for super case and the usual case. There are some. There is some coefficient which contains trivial zeros, so-called trivial zeros, which are just the theta alpha are the parameters. I introduced them somewhere. Sorry, maybe not, but they are related to this u1 minus u, essentially. So this is a fixed. Those are fixed zeros which has to be extracted from Bajanov-Reshetikhin determinant to render to get our transfer matrix. And the rest of this the rest of it will correspond precisely. This ratio will be precisely the polynomial of the power n, the number of spins in the system, as it should be. Now, it's interesting already here to compare this formula with the so-called Jacobi-Trudy formula for JLK/M characters, which is just this, which gives you the general character of the element G in terms of determinant with respect to highest weights, various shifts of highest weights, which are written here. It's the subindex, I'm sorry, where it goes up to a, the number of rows in the Young tableau, And the symmetric polynomials can be generated. These are sure polynomials, chi-s, can be generated just from this superdeterminant, 1 minus z, some generating parameter times group element G, just by expanding this superdeterminant. So this analogy, of course, is very striking. You see only, the only new feature is that you shift also the spectral parameter here. Here you don't have it in the character, so the formula simplifies. Okay, so we want to prove this formula, starting from R matrix. We constructed our transfer matrix. By this construction, we wanted to prove that it's equal to this. Now let's go to the proof of Bajano-Freshetykhin formula. This is a bit technical part, but actually every step is elementary. So for those who want really to understand our construction, just follow step by step this transparency, because we have to define this left co-derivative. We defined the group derivative, which we called left co-derivative. I'm sure mathematicians have some other name for it, because it's a very natural object. You differentiate with respect to the group or supergroup element G, any function, not necessarily invariant function. It can be just anything, a tensor. By doing the following, you shift the group element from the left by e to the algebra element, which is here. So it contains some matrix phi alpha beta and contracted with generators. You differentiate it, and you put down, of course, the generator. When you differentiate with respect to this matrix, you put down the corresponding generator. So that, but this is the definition, yes, and at the end you put phi to 0, it depends on, again, on G. Nothing is more simple, especially that these generators E alpha beta are very simple. I adjust this, yes. So, for example, in components, if you act just on the element G in fundamental representation, after simple calculation, you get the following. This I1, J2 are this and this index, and they're just going in cross, and I2, J1 are here. So it looks like a permutation of upper indices, yes, with respect to the lower. So that the general formula, in one more abstract way, will be the following. You act on G, and every time you open the indices, yes, this D is a matrix derivative. You differentiate every G in this sum, and the term somewhere in the middle will be, of course, a direct product. You split the product into two, insert the indices in between, and also permutation. You apply the permutation according to these rules. So, and now if you act on the arbitrary, on the same group element in arbitrary representation, it's also simple. You put down the generator within this representation. It's a product of generator times G, and also according to this formula, it is contracted with E alpha beta. So E beta alpha, E alpha beta, which for the fundamental representation would be again permutation as for our R matrix. So this is the main part of our matrix. This one is simple. So we rewrite this through our derivative. So we managed to rewrite this through our derivative D. So the R matrix in arbitrary representation lambda in the auxiliary space looks as simple as follows. U plus twice our derivative acting on the group element in this representation. So if there are questions here, because it's based on these trivial steps, after all, the trivial matrix differentiation. GL n group, GL k slash m group, it's very easy to differentiate, yes. There are general matrices. Okay. Now we continue this construction with rewriting the monodromy matrix. It is L here, yes, it's hidden a little bit behind. the monodromy matrix now will look simply as follows. We apply our operator, this operator, a few times in direct product, every time introducing the new spectral parameter, U1, U2, etc. We took this notation, U minus theta, this fixed inhomogeneity parameters, we call UN. In this interpretation, the transfer matrix without spins at all would be just the character, because what you do, you take the group element before acting on all this. You take the super trace, or trace in bosonic case, and you get the character. So the character plays the role of empty spin chain, which is very nice to my taste, because the character is a very nice object with which I worked a lot in the 90s, and of course it smells very much as matrix model stuff. And then if you act once, it is the transfer matrix of one spin. Yes, you open one spin. Every time you act, you open spin by spin. So for n spins, it will look like follows. This is the same derivative, but they are taken in direct product, because every time you have to open the indices. To my taste, it's very simple to understand. Okay, so we found it very useful to work with this representation of transfer matrix. Next step. Now we want to prove the Bajanov-Reshetikhin identity. By the way, one comment which would be in place here. You see, in principle, this is the determinant of operators, which is a bit funny. Yes, you ask about the order of terms here, but each term among n factorial terms is the product, of course, of commuting transfer matrices. That's why it's perfectly defined, this determinant, due to integrability. Okay, now let's do the proof for one spin to demonstrate everything. It's already sort of demonstrates the main point of our construction. So our formula, I mean the formula rewritten through our derivatives, left covariant derivatives, looks as follows. This t, forget about s for the moment. S is this polynomial, trivial zeros. It's just to compare with Bajanov-Reshetikhin formula. This t is equal to that in one spin case. This is the formula of Jacobi-Trudy for character, the standard one. And this is the derivative acting on the group element, and u plus 2d opens one spin in the chain. From the point of view of Bajanov-Reshetikhin, this is a determinant of symmetric representations. So we take symmetric characters, which are sure polynomials, act with the corresponding, with this derivative plus corresponding shift of spectral parameter, and take the determinant along the Young tableau. So we have to prove that this is equal to that, and extract. And the first step is to extract trivial zeros. We have to prove that this determinant contains Bajanov-Reshetikhin, I called it TBR, determinant contains all these trivial zeros, to factor them out. How to do it? And this is the most non-trivial point. You just take this determinant, this right-hand side at each 0, which you expect at u equals to k. And you notice that in this determinant there are two neighboring rows which contain, of course, symmetric transfer matrices of symmetric representations of the spectral parameter 2 and the next one of the spectral parameter 0. Yes? And now we can show that any 2 by 2 minor, if you multiply any 2 by 2, if you take any 2 by 2 minor, it's 0. And instead of T matrices, we rewrote it through our derivatives. So essentially, it's this identity. The spectral parameter is gone here because we took a particular point. It's a nice derivative 4 symmetric characters, for sure polynomials, which I don't know whether it was known before, but we easily check it by just remembering that this is the generating function for these characters. And essentially, we can, instead of using the characters here, we can multiply them by z to the, convert it to a generating function. We have these w's, generating functions here, and to prove it for that. And just using this matrix, using this matrix derivation, the differentiation, using this trivial formula, not that the indices of G here are open already. G is a matrix. We prove this identity. It's really trivial. And what is left, actually, as we know, for one spin, only the polynomial of, only the linear polynomial, the R matrix, the transfer matrix is the trace of R matrix, and it's a linear polynomial in U. We have to just to pick up the linear and constant term, which is very easy from this large U asymptotics. So here you divide Bajanov-Reshetykhin formula for this on this polynomial. It's better to divide term by term. Then in the large U limit, this 2 minus 2i goes away, and essentially the main term of asymptotic for U going to infinity is 1 here inside the determinant. Then you get just determinant of characters, which is the Jacobi-Trodi formula for character. This is the first term, U times character. And the second one, you have to expand up to 1 over U. And of course, it will happen that the derivative acts only on one term in each of n factorial terms in this determinant. So you'll get just the derivative. You can pull this derivative out of determinant in this approximation due to the linearity of the action of derivative. Well, you restore this formula from the asymptotics. So it was already nice for us to see how it works for one spin, the Bajanov-Reshetykhin formula. And we thought that with Pedro that we would need one day more to prove the general identity for n spins, but it appeared to be the next non-trivial step, which I hope to describe now. Here you see, if you take this transfer matrix is a trace of this R matrix. So if you take the trace, what do you have? This is just proportional to unity. Trace of group element in representation lambda is character, yes? And you just take the trace of indices, and then you have the derivative of this character. Yes? Now, here, you also don't have any indices. That's the nice point of this construction. You have characters, you have some, of course you have indices, because the derivative have indices, yes? But since we know that all the terms commute, we can still write the determinant. And these are still operators, but they're all commuting. Then this is precisely this times this, for example, minus this times this, or one of these terms. S1, S2 are general here. So again, here you have an open index which is in direct product with this open index, etc. I'm not sure I explained it, but each operator opens a spin, and it corresponds to the matrix. This. Yes. Yeah. But you see here, the one spin case is simple because you have only because everything commutes. You can, by one differentiation of D, you open only from this invariant, you open only a couple of indices. Essentially, you have a function of G just in fundamental representation. So of course everything commutes because this and that depends on, this is the function of the same matrix. Although you have to multiply here. The rest is, just this identity. You can view here G as a number because There is nothing else here for one spin. Okay, and so we now go over to the proof of n spins. And the beginning is simple. You take the general formula now for any number of spins, which is hidden somewhere there, n spins, and take it, you want to extract trivial zeros, which are now more complicated. I introduced it somewhere at the beginning. Where was it? Sorry. Here is the formula. It's a double sum with respect to the number of spins, with respect to the labels of spins, and also A is the size of the Young tableau, the vertical size of the Young tableau. So we are still able to extract where we are here. So we still write two we again take two neighboring rows in a particular point of expected trivial zero, and we get this identity. Now, one step is needed to get rid of all these TNs. Essentially, we can easily prove that if we this formula, it's enough to prove this formula at theta n's equals 0. It's checked by induction. Say you expand with respect to each theta, and you observe that there are only linear polynomials in theta. So you observe every time that either you have the previous formula with one spin less, or you have the derivative of this formula, this d derivative, left covariant derivative of this. So it's easy, and it boils down to the case theta n equals 0, which is the following nice identity. Also, for the generating function of characters, w of z. Of course, and this is the key identity. If we proved it, we proved the Bajanov-Reshetikhin formula as is demonstrated here in analogy with one spin case. But this is going to be a bit harder. This is a very nice identity. Already you see, concerning the indices, it contains n times n open pairs of indices. This is a matrix relation, and you multiply it in the space of these indices, these two blocks. On the other hand, it looks very much like a bilinear identity, and it should be probably some version of Hirota equation for discrete KdV. Say character, which is generated by this W and then Jacobi-Trudi formula, is known to be KdV tau function, discrete KdV tau function. So this is another identity for characters, symmetric characters. It should be somehow related to KdV. In fact, it seems to me that even Bajanov-Reshetikhin formula has some classical origins in classical integrability of such integrable hierarchies like KdV or Kp. Although the object is a bit more complicated, you have many open indices here. But probably you can transform them into some generating functions if you combine it with some. You can hide it into some dependence on other matrices, which could mean of the times of Kp. Okay, now the next step, which I should already only briefly mention, is that we can extract the remaining polynomial of nth power, where n is the number of spins, by the same trick from asymptotics, by sending u1, u2, etc. to infinity one by one. We will actually pick up all these terms. So this is for the form how it looks for u1. It's very easy to continue and to prove that, in fact, after dividing by Bajanov-Reshetikhin determinant by trivial zeros, we restore the transfer matrix, standard transfer matrix, in our notations through this left covariant derivative. Okay. Now the proof of the main identity. I should come back to this identity and to show you. This is this identity, and it always contains this curious combination, 1 plus d and d. So to some extent we should show that they commute, because here 1 plus d acts on w of generating parameter z1, here of d on z2, and this here vice versa up to some trivial factors. So we have to consider each of these derivative, multiple derivatives, 1 plus d to the n and d to the n separately, and to see what it is. So let's use our matrix rules. We act n times in the direct product on the generating function of symmetric characters, w. The first derivative we already saw. This is just differentiating e to the trace log of 1 minus gz, which gives this. In indices, it's also very simple. You open a pair of indices, because G is a matrix. Let's introduce these pictorial notations, otherwise we understand nothing in the general construction. So if we act by D on W, already D has a couple of indices, so we sort of keep them here in mind. And if we differentiate, it's this formula. We open this line, which has a couple of indices, upper and lower, and the red line will mean always that you have this factor with 1 minus gz in the denominator, and what is important, it's red because you have gz in numerator, because there will be also one more color without gz here. Okay, this is the first derivative. Now let's act twice. So we have here, as a result, this term, this factor. It's nice to know how to differentiate it, because we already know how to differentiate w of z. So let's differentiate this. Let's differentiate this. In abstract notations, we have these two factors now, each with its own indices, and then we apply permutation. So the upper indices should be permuted. Here we have this and this, and this and this, but here this and this are permuted. In components, it's also easy. You see, you differentiate. It's normal. It breaks into two. Because this differentiation breaks it into two ratios. Gz appears only to the right. It's due to the left derivative. And these indices, in and ia, are I think we forgot to permute it. They should be permuted. So you see that if you act by D on W, you open a red line, which is essentially this factor. But if you act D times D on W, of course, you open the second red line. This is a possibility, but you can also act on this red line, yes, now. And you get this, the following construction. This is a red line with GZ on the top. This is the dotted, I think, blue line or green line. I don't see well the color, without GZ. So the color corresponds to this. And the fact that they are crossed is just permutation, which I think we forgot here. Here it's IN, here AI. Is it permutation? We permuted the lower indices. Okay, sorry, it's the same. Okay, now if you have many, so it's in a more abstract way. If you have many open indices, the action on this particular term is the following. You see, according to this, you obtain this dotted line. From here you obtain red line, but the permutation happened, yes? When you act on red line, it's the same as acting on blue line, because it doesn't matter whether we have GZ in the denominator or not. and you get the second line, and they are crossed due to permutation. Now, if we act 3 times, you get all possible terms of this kind. You get all possible vertical red lines, and all the blue lines are, all the dotted lines are tilted to the right. All the red lines are tilted to the left. And essentially, you get all possible combinations of this kind. These are like Feynman graphs, not as complicated as Nelia's graphs, but by the way, having more or less the same origin. We don't have, of course, the momentum integrations here, but the index structure of supergroup is here. Of course, things are simpler here. Okay, then now we have to work out the same for the operator 1 plus d. Essentially, you see that when you differentiate it, you don't have gz in the denominator, so in the vertical lines will be blue. I probably have to speed up to tell you the rest of the story. And then essentially, you get the same graphs, but due to this fact that there is not gz on the top, when you differentiate w, blue lines are vertical now. The rest you get the same. Tilted blue lines on the red and tilted blue lines on the left tilted blue lines, red lines. Okay, and now we compare these 2 results. What do we see? The difference only is in vertical lines. Here, all the vertical lines are red. Here, they are blue. But now it's easy to transform one picture into another by tilting. You see, you can tilt all this to the right, which means that you make cyclic permutation of these upper indices. Then the blue lines will be inclined like here to the right. Red lines, say this red line will be now straight after this tilting, and vertical lines will be only red lines as it is here. And the only defect is due to the periodicity, yes, because let's, for example, consider this picture. If you tilt these indices to the, if you tilt it to the right, you should compare it with this. No, with this. So these 2 blue lines will be this and this, but this will be too far here. Normally, this should be here. By periodicity, we put it there, but we have to also multiply it by gz, make it red, sorry, which means the multiplication by gz here, as I said. So the last line should be always dropped to, should be always by periodicity dropped to the left and made red. Now it's very easy to identify these 2 things. You multiply it by the permutation, say the upper row you multiply by permutation, here you tilt to the left rather. And also you add gz for the last one. Then they are completely, after this identification, they are completely, after this multiplication, they are completely identified. D to the 3rd power of w and 1 plus d to the 3rd power. And this completes actually the proof of Bajanov-Reshetikhin, because if you multiply, essentially you have to multiply the inverse by the inverse of this matrix, one of them, multiply them, and at the end you will get this identity. Where is it? Sorry, I lost it. It's really far. This identity. So you multiply this times this, and somewhere in the middle, this extra matrix will cancel with the inverse, and also here as well. Okay, so we proved this identity. Now the formula of Bajanov-Reshetikhin is proven. And, how to get some miles out of it? Let's now, first of all, let's write the Hirota equation for the representations which look like rectangles of the size A times S. This is symmetric, this is antisymmetric direction. So we'll denote these T transfer matrices as A, S, and U. They have only 3 parameters. Just because of the determinant formula of Bazhanov-Reshetikhin, using the Jacobi relation for determinants, we can derive the Hirota equation. It's a very easy step. Actually, Jacobi relation, which I learned only being already quite old, should be taught, I think, in the course of linear algebra in the first year of the university. It is so beautiful and so useful in many cases. You see, if you have the determinant of this size, I mean, if you have a square matrix of this size, you compute the determinant. This dashed is determinant of. Then you can strip this matrix of these 2 columns and these 2 rows, upper and lower. Again, compute the determinant, you multiply them, and then you do the same here. You strip the last row and the last line, here the first and the first, minus this natural thing, when here it's in this direction, here it's in this direction. And this is true for any determinant of any table of numbers, yes, which is very funny. And just plugging in the Bazhanov-Reshetikhin with some appropriate definitions, you get this. This is the discrete classical dynamics describing the quantum fusion, which I promised. It's given by this equation. Now, I go fast through the rest of the construction. This is the short review of representations in supergroup of superalgebras. The Young tableaus, which is inverted here. I don't know why we now always it should be reflected with respect to this line. Here is the most general super Young tableau, which lives in the area which is called fat hook by mathematicians. It's due to this mixed nature, bosons and fermions, including bosons and fermions of the tensors in this theory, bosonic and fermionic components. So all Young tableaus should be somehow within this fat hook. And if they touch this corner, these are long representations, the typical representations. If they don't touch, they are atypical. Essentially, our construction is for both, although one should look at the details, these continuous labels, etc. We know something about them, but it's not for this talk. Now, the rectangular representations are of this kind, yes, or they can go here, etc., up to infinity in both ends. And we have the dynamics with specific boundary conditions. All our Young tableaus and corresponding transfer matrices, which are non-zero, are completely within this fat hook. Now, actually, I don't speak about the details of boundary conditions. We can solve this Hirota equation, which we did in our paper with Zabrodin and Sorin. We can solve and completely restore the whole multitude of TQ relations of Baxter, generalized, of course, in this case already. I think there is not much left after that of generality. So I will show you just the result of this construction. Essentially, it's a generalization of tricks with characters. You introduce this generating function of symmetric representations, very much similar, generating operator of symmetric representations, very much similar to the ones for characters. Only here you would have this z parameter expanding in symmetric, the length of this symmetric row, and you have this shift also by s. And this is a shift operator by 2s units in u in spectral parameter. So I called it big W And this is true for supergroup JLKM. Now, to express it through, I mean, I better show this generating function. Where is it? You see, it's here. This is the formula which I've shown. W is equal to this, but generalized to the quantum case with shifts of spectral parameter. Now we have to show something like this, yes, that this is equal to that for the quantum case. So in fact, you introduce the so-called shift operators. This one will be associated to the vertical shift and this one to the horizontal shift. In the nesting space, I don't have time to explain, but these are shift operators of the same nature, but the coefficients depend on the Q functions of Baxter, which are defined here. These Q functions have the double index because you have the group GL K/M, so it's natural for Q functions to have two indices because the nesting procedure is nothing but let me show here, but this sort of Gelfand-Seytian procedure. On each step, you lower the rank of the group. GLKM goes to GLK-1M. Then you can lower this index, for example, M-1, etc. So you have, thank you. So remember these operators. Now, in terms of these operators, we give the result for this generating function of transfer matrices of symmetric representation, which is here. So you should imagine the nesting space, the Km are indices which are going from K is going to big K and M is going to big M, the rank of the group, two ranks of bosonic subgroups. And imagine the path gamma, which goes from the upper right corner, any path, going to the left corner. And you make up the ordered product of these operators, of these shift operators, along of this path. Of course, nothing should depend, the results, the final results shouldn't depend on the path, but the intermediate representation, and in particular the set of Q functions of Baxter which you choose. In each point here you have a Q function with corresponding coordinates Km. It depends on it. And the change of the path is the famous particle-Hall duality, fermionic one, which was, by the way, for this case, already observed by Tsuboi in '98. And this is essentially almost everything about dualities, the freedom to choose the basis of generators in the group. But there are also interesting bosonic dualities which we didn't take into account, which are now taken into account by Gromov and Viera in the recent paper. So essentially we have now the list of all dualities. And this formula gives you all the generating function of all symmetric transfer matrices. Then if you use the Bajanov-Reshetikhin formula, you complete everything. You build really TQ relation for any representation, any of your favorite representation. It's very easily, you can create immediately algorithm on Mathematica, which I think Kolya Gromov even did, and generate any favorite TQ relation which you like. I think it was not known in the literature. Every time you painfully constructed by algebraic beta ansatz, I think here it works much nicer. And I'm almost finished, sorry. Now, we have to explore the independence of the result of the path. For example, here we have this path, and we want to change here a little bit. Instead of this path, we take this path. The result is invariant, and that's why we have sort of a zero curvature condition on these operators here inside this square, which is shown here. These are, I remind, these shift operators, vertical and horizontal, and they depend on Baxter functions. When you write this condition, you arrive at the following nice formula only for Q operators. which we call QQ, QQ formula, QQ bilinear relation, which of course also smells like Hirota. It's a kind of Hirota also. Now, by construction, both transfer matrices and Qs, Baxter operators, are polynomial. And it's very easy to infer the nested beta ansatz equations from this. You just take this relation at zeros of each of 6 Qs entering here, and you easily combine it into the set of nested beta ansatz equations, which of course with a specific choice of our basis, of our path, this path, they are constructed according to the Cartan matrix of this Katz-Dehmken diagram. So this zigzag path representation is very useful, by the way, I think, for the study. Okay, I think it's actually I'm arriving to the conclusions and prospects. So the main result, the results of these 2 papers are that we proved Bazhanov-Reshetikhin formula for general fusion. I wonder whether some physicists know some proof, mathematicians know, but they have to explain us. When I asked Reshetikhin whether they, with Bazhanov, proved it from first principles, he said, no, only from the second principles. So when I asked, when I asked Bazhanov, he said, oh, we had somewhere the proof for GL3, which probably can be generalized. So and then I should, of course, mention Cherednik, I mentioned already, who made a couple of very important contributions to the subject in the late 80s, early 90s. And his construction probably is very interesting, but we were unable, even with his explanations, to understand it. There are some papers which, there is a paper of the French mathematician Hernandez, which claims to reproduce Hirota equation, which is not everything, of course. It's a particular case only of rectangular tableaus. So it's interesting, but our proof is elementary. Every step is elementary. Okay, then we reproduced all the multitude of TQ relations of Baxter for general supergroup GL KM K/M supergroup, new QQ bilinear relations, and fusion in the quantum space, by the way, we also did in our paper with Zabrodin and Sorin. I had no time to explain. There are general formulas for it. Now, of course, it's nice to generalize it to everything. Non-compact, I think it should be simple, because non-compact characters, after all, it's easy. Then there are interesting mixed covariant contravariant reps. There is a challenge. Then OSP groups. Then trigonometric case already it seems to be doable. Elliptic maybe not doesn't exist even for supergroups. Then of course my main interest now is to apply all this to non-standard R matrices like Hubbard or SU2/2. The same Hirota equation works, of course, for the bound states of the kind of Nick Dory encountered. It's left to guess the boundary conditions, and the work is in progress with Zabrodin and Suboy. Then probably, okay, but potentially it's a very powerful tool for studying supersymmetric spin chains and 2D integrable field theories, including various classical limits. By the way, classical limits are very easy to do and restore the algebraic curves from this formula. From here, it's really trivial. And all this smells as matrix models, as I said. So potential matrix model applications can be thought of. And we should understand better the relation to KP and KDV, classical KP and KDV, I underline. And it's a nice alternative to the Leningrad school algebraic beta ansatz, which I invite you to look at. Thank you.
One question.
TQ relations also come up when you do, say, boundary problems like the condo problem or things like that. So these generalized TQ relations, do you know what they might correspond to in that context?
Not yet, of course. This activity is at its beginning, but I suddenly thought yesterday, preparing my talk, that why not to use this this twist element G to break up the chain and to use it for the boundary problems. So it's the only thing which I can say for the moment. But I'm sure it can be generalized to the open spin chain, open spin chains. Yes.
Okay, I think we'll break the lecture. So, thanks all.